And Johan is going to tell us about Palmgren's Intuitionistic Ramified type theory. So
yes, thank you, Henrik. Yeah, so for you, those of you who don't know me, my name is Johan Lindberg. I was a PhD student of Eric's until he passed away last year. And after that, Peter Landstein became my main advisor. And today I will talk about a formal system that Eric introduced called Intuitionistic Ramified type theory, which I've done some work on as part of my PhD thesis, which I will defend later this semester, by the way. And this talk will mostly be expository due to time constraints, but I'll see how much I'll be able to tell, but I'll mention something about the work I've done and future work. But before I start, I would like to say a few words about Eric. So I have some faint memories of Eric from my time as a student in Uppsala, where he was a professor at the time. However, I did not know any of his research at that time or what he was up to or doing, I should say. In fact, I didn't know much about logic at all at the time. I later took a course he gave at Stockholm University on computability and constructive mathematics. And the ideas I encountered there affected me quite deeply and sort of set me on a new path. And hadn't I taken that course, I'm not sure if I would have pursued a PhD in mathematics. So in this way, at least, Eric affected my life in a quite significant way. Eric was a widely knowledgeable researcher and a very generous person, and I'm thankful for all the discussions we have and the knowledge he shared. So thank you, Eric, if you're listening. And with that, I think I'll resume with the talk. So yes, some introduction. So this formal system, which I'll call IRTT, it's much shorter to say, it is introduced in this paper, a constructive examination of a Russell-styled ramified type theory. It is from 2018. By the way, I hope, do you see yourself on my screen or no? Okay.
We just see your slides, it's good.
Okay, good. Actually, there is an earlier publication introducing this theory, which is much shorter. It's from 2008, but I'll refer primarily to this paper. And this is a type theory similar to that of In Principia Mathematica with intuitionistic logic and includes a version of the infamous reducibility axiom. And in this paper, Eric shows that this version of the reducibility axiom is constructively meaningful, as he gives an interpretation of this theory in Martin-Webb type theory using setoids. He also shows that intuitionistic logic is essential because if you add classical logic, it collapses the ramified type theoretic structure from an extensional point of view. And in this paper, Palmgren also writes that he expects this to give rise to a natural notion of a predicative topos. Sorry, predicative elementary topos, I should say. So it is from this perspective that I will describe this theory. And from that point of view, I think it's more fruitful not to think too much about this or any relation with the stuff in Principia Mathematica. Rather, it is perhaps better to think of it as a theory which you extract from the setoids in Martin-Webb type theory. And you can work more directly with this theory, so you don't have to use the setoids directly. And this is an idea which is also expressed by Maietti in her 2009 paper on minimalist foundations. Okay, so let's look at how this theory looks like. But first, I will describe the syntactic counterpart of elementary toposes with natural number objects as what is sometimes called intuitionistic type theories or local set theories. So this first name, intuitionistic type theories, is used by Lindberg and Scott in their book, whereas John Lane Bell calls them local set theories. I guess this first name has more or less been abandoned now because it's easily confused with Martin-Webb's type theory. In any case, these are theories in many sorted first-order intuitionistic logic, and I'll next describe what the sorts are, or types, as I will call them. So they are inductively defined, and you start from the unit type and the type of natural numbers. And then you close them under products and power types. As term-forming operations, you have an element of unit type, you have projections, pairing, and comprehensions. And the zero is an element of the type of natural numbers, and you have a successor operation. As relation symbols, you have equality for each type and a membership relation for each type also. And as axioms, we have extensionality, comprehension, and what could be called the piano axioms, stating that elements of the type of natural numbers have the right properties. So this is a description of the most basic local set theory, which I would prefer to say. There are, however, some few more axioms stating that all elements of the unit type is equal to this star here, and that projections and pairing behave in the expected way. Yeah, so this is the most simple local set theory. In the more general case, you have, could have a set of basic type symbols to start with here, and a bunch of function symbols and relation symbols and some additional axioms. Okay, so if you have such a local set theory, you can obtain a topos by taking the closed terms of power types as objects and the functional relations between them. So this means that the objects essentially are a comprehension term like this. So this is a variant of the syntactic category of the theory. And if one has a elementary topos, it has an internal local set theory such that the syntactic construction is equivalent to this topos you start with. And yeah, as we saw, local set theories don't have dependent types. And another way to describe the syntactic counterpart of elementary toposes using dependent type theories were given by Maietti in 1998 and 2005, as we saw earlier today. Okay, so let's look at this Intuitionistic Ramified type theory. So the description is very similar. Describe the types inductively, starting with a unit type, a type of natural numbers, and close them under products. And now we have ramified power types. So we have index k here. It's a natural number. And the term-forming operations are, again, similar. You have an element of unit type, you have projection pairing, and something called ramified, or I call ramified comprehension, which I will return to later. Series, again, an element of natural number, and for simplicity, I throw in addition and multiplication here, in addition to successor. As relation symbols, we again have equality and ramified membership relation for each type and number k here. And as axioms, we have extensionality, comprehension, and again, for simplicity, we have all the axioms of Heiting arithmetic here. And now we also have Palmgren's reducibility axiom here, which I abbreviated FRA. So this is not quite the whole, it's not really this simple, the whole theory. We will assign every formula a level, so that if you have a formula of level k, it describes a subset of one of these kth power types. But before doing that, I will take a short detour and say something about setoids. So I think one can think of these types as setoids, or the intended interpretation, I would say. So before continuing describing IRTT, let's recall some stuff about setoids. So we have seen them before. They are a type equipped with an equivalence relation. I mean, formally, you have proofs also that this is an equivalence relation, but it's usually written as a pair. And you can form product of setoids and exponentials. And so how does this product look? Well, the underlying type is the product of the underlying type of A and the underlying type of B. And to check that two pairs are equal, you check that that their components are equal. And the equality on this exponential setoid is pointwise equality. Okay, so now consider a setoid in a cumulative hierarchy of universes, externally indexed by the natural numbers. Then we say that such a setoid is an NM setoid if the underlying type is in UN and the equality predicate maps into the universe UN. And we note that the omega k, the setoid with the kth universe and provable equality, logical equivalence, is a k+1 k setoid. And if A is an NM setoid and B is a KL setoid, then the product setoid is an, and this subsymbol or it notes the maximum of two numbers. So this setoid is an N max or N sub K and M sub L setoid. Yeah, so we took the maximum of the level of the universes where the underlying sets are, and underlying types are, and then the maximum of the index of the universes where the equalities are. So if N is an NM setoid, then the exponential setoids of maps into omega k is a setoid of this form. So why? Well, the universe here is in the k+1 universe, and A was in the nth universe. And to form the equality, we have to quantify over the type of A and check that the result is equal in the kth universe. So that's where this number comes from. Okay, so with this in mind, let us continue the description of IRTT. So this is the same slide I had earlier, sort of to continue from here. Sorry, I will just clicked on the wrong thing. Okay, now let's continue. So we will assign a level to the types of IRTT. So we define the unit type and the type of natural numbers to have level 0. And we define the level of a product type to be the maximum of the component. And then the level of the power type to be the level of A sub with k+1. And the equality level of 1 is 0. Equality level of n is 0. The equality level of a product is the maximum of the components. And then the equality level of the power type is the level of A. And sorry, there's a typo. It should just be K here. Just K. Okay, using this, we will assign a level to formulas the following way. So the level of the true proposition is the same as that of the false one, namely 0. The level of this equality is the level of A. So given what I've said so far, you would have expected this to be the equality level of A, but I will return to this shortly. The level of this atomic proposition is K. And for the propositional connectives, you take the maximum of the two components. And for the level of a quantified formula, you take the level of A and you take the maximum with the level of phi for universal and existential quantification. And using this, if K is a number greater than the level of phi, then this comprehension term will be of type pk of A. So what will happen is that in the language, there will be a formula representing equality of the level of the equality level of a type of A. So this does not really matter that or this apparent mismatch with using the level of A here. Okay, so we have a setoid model of this theory. Types, as I suggested earlier, are interpreted as setoids. You take the unit type to the unit type in Martin-Löw type theory. Yeah, so maybe I should say this is the type on the type theoretic side. We have a cumulative sequence of universes closed under the standard type constructors. Yes, so the unit type is sent to the unit type in type theory with the identity type as a quality, similar for the natural numbers. The product type is taken to the product of the setoids. The power type is taken to the exponential setoid. And this interpretation works so that formulas phi of level k are interpreted as types in the kth universe. And terms of a type A are interpreted as, terms of a type A are interpreted as elements of the underlying type of the setoid A star. In particular, a comprehension is interpreted as a lambda term. And in a similar fashion, one could also give a model of IRTT in homotopic type theory, where one interprets the types as H sets, and where this, where the propositions in the kth universe plays the role of omega k. So in this case, it will more precisely be a set together with a small equality predicate. So not just an H set, if one wants to be precise. Okay. So I haven't mentioned the functional reducibility axiom yet, and I will now describe what it is. So for any sets X and Y and F, if F is a map from X to Y, so a functional relation, then there is a set G of a certain power type, which is extensionally equal to F. This is what this formula says. And this number K is on the following form. So what you do is you take this L here, sort of the height this set X has over A, and then you take the maximum with the equality level of this type B here. So to give some motivation, consider the case if L and M are 0. So X is essentially the type A and Y the type B. And F is an actual function from A to B, of which F is the graph. Then we can form this set, and it has this level. And in fact, one could, as I said earlier, you could replace this equality with a formula in the language. So you actually could describe this set from an extensional point of view using, well, when having the equality level of B here. So if you could always introduce a function symbol when given a functional relation, something similar to this must be true, right? And this is sort of what happens when you check that this is actually valid in the setoid model, that you could always sort of extract the image of this map as an actual function. Okay, so one might wonder if this use of these equality levels are actually necessary. It seems somewhat complicated to assign the type both a level and an equality level, but let's look at an example here. So we suppose we're given a set X like this, and I will now describe, or I will now show that IRTT proves the following. So what does it say? Well, it says that if we, for every X of the type A, has a way to check, sorry, we have a truth condition or something similar to check whether this element is in capital X. So then we should be able to extract a function, or sorry, extract a set S extensionally equal to X at this level M. Okay, and how do we show this in IRTT? Well, suppose we have the antecedent. Then this set here will be a map from the set of all elements in A to this guy here. And if we recall from the functional reducibility axiom, we could bring this down to a certain level, namely the level where you took this number here, and you took it to with the maximum of the equality level of this type here, which is M. So we obtain a G from FRA on this form, extensionally equal to F. And we can now form the set S of all the elements X, which are mapped to the total set, total power subset of 1. And for this, the following holds. So if we had not had the sort of equality level of this guy available, just the ordinary level, it would jump us up to M+1. So at least this argument would not have worked. Yeah, so yeah, maybe I should have said from the start, if you have any questions or comments, you are free to interrupt me. Yep. Let's see, how much time do I have? So can you remind me, when was I supposed to finish, Henrik?
Right, you started about 9 minutes late, so Peter de Bière should start in 15 to 20 minutes.
Okay. Then I have time to look at the next slide. So one could also consider a version of the fullness axiom from constructive set theory in this setting. So, and here's a version. So suppose we're giving a total relation from, so total relation F from X to Y. Then the axiom says that there is another total relation at a certain level contained in F of this particular height. So all these numbers comes from checking when this holds in the setoid model. And of course, this implies a version of the functional reducibility axiom, because every functional relation is a total relation. But if we look at the argument previously given, suppose that we have a way to check that an element is in X at level M here. If we would redo the argument, we would, the level of A here would be, get involved here. This is not quite, we cannot, does not appear that we could replace the functional reducibility axiom with this fullness axiom. Okay, so how do we, if we want to look sort of more at the categorical properties of this, how do we proceed? I guess there are some choices to be made when setting up this this category. For instance, one has to decide to what extent maybe one wants to quotient objects, and it could also be the case that one has a close description of a set X, for which one could prove that there exists a set at a possibly smaller level. So we could be in this situation here, that there is and so what I've done in my work is I've taken the approach of considering a category of triples, where you have a type, and then you have a sort of a description of a set, and then you have an element, you have a number, M, which the theory proves an extensionally equal set exists at. And with morphisms, you just take functional relations. And maybe not so surprising, perhaps, but you can show that the category you take from or construct from IRTT in this way is a pi pre-topos with a natural number object. So this result in itself may not perhaps be surprising. Maybe it's more interesting to see actually what level the constructions end up at. What level does the dependent product end up with, and so on. However, I won't go into that detail here. There will just be a bunch of numbers which perhaps won't say very much, but in some cases also, for instance, with the proof that the expected natural number object has the universal property, you sort of have, or I had to give a new argument, at least when compared to the ones given in the book by Lindberg and Scott and Bell, which seems to use the impredicativity of the power set operation in an essential way. But this category also have a kind of K-level subobject classifiers. But to find a nice sort of categorical description of the theory, which has this have a kind of local set theory as an eternal language, is still left as a problem. But next, I would like to say something about a way to represent inductive definitions in IRTT, and this was actually proposed by Eric in unpublished notes. So, and this could be this could be seen as a suitably adapted variant of formulations of inductive definitions given by, for instance, Peter Axel. So in the present setting, we could say that an inductive definition consists of an underlying set X and a set of rules. And then we have a relation between rules and conclusions, and then a relation between rules and premises. So we could, given this, we could say that a set containing X is declosed if the following holds. So it says that if X is the conclusion of a rule, and if all premises of this rule is in S, then also X is in S. Maybe I should have written that X is in S here rather than S of X, but that's what I meant. And then an axiom that Eric proposed was the following, called the principle of general inductive definitions. And it says that for any inductive definition of this form, there is a smallest declosed set of a certain power type, namely with K equal to this number. So it's the maximum of these. So again, this this number comes from when you interpret the theory in the setoid model. And if the type theory has W types, then you could verify that there is a smallest set at this particular level. And yeah, in my work, I had investigated when the construction of the category of sets in this extended theory is form a pi W pre-topos. And to show that, I needed to use a variant of the union replacement axiom from constructive set theory. And yeah, with this extension, I could show that this was the case. Okay, so I see that I've gone somewhat faster than expected, but I will say something about some ongoing and future work. So one could also consider more general external ramification bases or indices. So IRTT is externally indexed by the natural numbers, which are the indices of these power type operations. One could also consider more general structures. And in particular, one could even imagine a category of some kind of ramified toposes over various bases and morphisms between them, although this is a bit speculative. But in this way, at least, if one has sort of a degenerate ramification, this could be a way to capture the impredicative elementary topos as a special case of some, a kind of ramified toposes. But this, again, this was a bit speculative. There are several more things to sort of clarify. For instance, I would like to show a conservativity result regarding extensions with function symbols and type symbols and so on. Yes, as I mentioned, giving or finding a nice sort of categorical description of what I call a ramified elementary topos. And then perhaps the approach or an approach with some kind of algebraic set theory is the most useful. I'm not sure, but it would be nice to clarify connections with other approaches. And one could also consider variations of IRTT with perhaps other type constructors, for instance, having a coproduct type constructor. As it is now, when you construct coproducts using power types, has some sort of or slightly undesirable consequences in that it bumps up the level of the coproducts in a certain way. But if I still have some time, I believe, so maybe I should say a few words about other approaches to predicative topos theory.
If you want to leave some time for questions, you can make it quite quick.
Okay, okay, maybe I should stop there. If there, we'll see. If there are no questions, I could say a few more words about other approaches, but because I can't see the chat right now if there is any questions. But okay, let's stop there for now.
Okay, so thanks, Johan. And questions?
I have a question.
Mm-hmm.
If we go to this inductive definition, yes, it seems that the initial inductive set that you get, its ramification index does not depend on the ramification index of the set of rules.
This N here, yeah.
Yeah, could you say something about that? Why it's independent of that?
Let's see. I don't have a good. I mean, it doesn't depend on the number L either here. As you can tell. So what happens is that you form a W type over the premises and conclusions in the type theory. But yeah, I don't have a good intuitive, or how do you say, like conceptual explanation of why that is the case. But I mean, I have, yeah, it's a good question. I've written out a very explicit proof in my thesis. But no, I can't give a good conceptual. No.
Any other questions?
I have a question. It's Steve.
Mhm.
Are you there?
Yep.
Okay. I have a question about the motivation for the ramification. The old modification was this kind of predicativity based on the vicious circle principle that Millie already mentioned.
Mm-hmm.
And I suppose that that is certainly satisfied in this system. You can kind of see it. But there was another motivation, at least after the fact, which Russell was often criticized for, and that was there was a kind of built-in syntactic interpretation. You could confuse the values of the variables for the formulas of the system. And maybe a way of expressing that in more modern terms would be something like each level has can be constructed as a syntactic category of the previous level or something like that. Mm-hmm. There's a kind of built-in syntactic stratification in the formulas, which gives you an interpretation for the next level up. Or maybe another way of putting it is when you add a new level, it doesn't add any new stuff to the previous level. That's again a kind of predicativity or vicious circle principle. Does any of that ring a bell with you in terms of some intuition for the system?
Well, to form in this comprehension principle, to form well, it's built in that you cannot, when we form certain subset, it can only talk about stuff that happens below. If that was sort of what you were asking, not sure.
No, that's not exactly it. But my question is not very clear either, I think. So I just thought you might have some. I mean, what motivates these rules? They seem kind of arbitrary unless you have some other conception of what you're doing. And I think Russell's conception was he was looking at the syntax of the system, and from that, he was deriving the rules for the stratification and so on. Is that all there is to it?
Well, I mean, like I mentioned earlier, you could sort of see it as you extract a theory from the behavior of the setoids, and you could see these as a kind of if you think of formulas as the condition for forming a set or the values of a characteristic function or something. And for instance, that the level of for these propositional connectives corresponds to that you stay within the same universe. This level regarding the membership predicate corresponds to, well, if S is a kth level subset, it corresponds to having a characteristic function mapping into the kth universe. And sorry, no, okay.
Yeah. I'm agreeing with you.
Okay. So that if you sort of would sit down and write down the rules in type theory for what happens, this is more or less what you get.
Maybe a way of sharpening the question would be to say, can you build a syntactical model of this system, which will then model a system with another level at level omega?
I don't know. I haven't thought about that.
Okay. Maybe that's a way of sharpening up the question. Okay, thanks. It's a very intricate and fascinating system. I think Eric's work on this subject was great, and it's great to see you pursuing it further. It's definitely worthwhile, I think. something that's
can I
fascinating
just
people
say
for
a
100
few words?
years.
Yeah, when you see this for the first time, and especially because there's not so much time, there's a lot of numbers and indices and stuff going around, but having worked on it for quite some time, although I don't feel like I've sort of have understood everything that's going on. It's quite a nice system to work with, and yeah, I had some. I guess I don't have time, but thank you for the questions, Steve.
Yeah, sure. Let me just mention, you must be familiar with the paper by Gödel, which is called Russell's Reasons for Ramification. Anyone interested in ramified type theory should read that paper.
Okay, let's thank Johan again.